Hi everyone, I'm so happy to be here. So I don't have a clicker, so I'm going to be walking back and forth, but I'll try to keep my eye on all of you. Okay, so who am I? So thank you for the introduction. I super appreciate that. So I used to be a GP and I work as an epidemiologist, well, occasionally, but I mostly earn a living by doing Rust development with a bit of Python here and there. As I have just been introduced, I have founded a company called Clinical Metrics. We basically do simulation software for training medical students and doctors to manage a busy emergency room, which I think we can all agree is quite important and highly stressful. And we actually wrote the back end in Rust because we needed a performance improvement. But I'm here to talk about epidemiology. Okay. So this is going to be a slightly different talk because I have to do a bit of introduction about what the problem is I'm trying to solve, which involves us learning a little bit about epidemiology. And are there any epidemiologists or statisticians in the room? Okay, so I could tell you anything and you'd believe me. Excellent, I love that. We're going to be talking about some simple functional examples, how we used it, how we kind of put it all together, and some lessons learned. I'm going to preface this by saying I'm not a functional programmer. I'm just someone who sort of accidentally adopted the functional style in some ways, and you're going to see the trade-offs that I've made with one of the open source packages that I'm involved with. Okay, so what problem are we trying to solve? Okay, so epidemiology is the study of disease in populations. So I'm an electronic health record epidemiologist, which means that I'm dealing with huge data sets. So not epidemics so much, but, like risk factors for developing diabetes, which patients die after having a stroke compared to other patients. And we have to deal with huge amounts of data. Okay, so what do we want from our scientists? Or from anybody who is doing research? We want the data to be, accurate. We want the results to be accurate. And for me, what that means is if I give you some code, which did my statistical analysis, and then I give you the same data and you run them together, you run the code over the data, you should get the same results. Now that sounds fairly trivial, doesn't it? Like that is what you think everything should be. That is in fact not always the case. I would say probably epidemiology and sort of health stats in general, probably about 20 years behind like modern software engineering. So they're using statistical code to write their analysis, but they're not necessarily using kind of modern software techniques to do so. And then the third point here is something I'm really interested in, which is if you have any code, okay, it has to be believable. So we're setting a higher standard, I would say, than say in a company. We write some code for a company. If it vaguely looks like, okay, that's correct, we might believe it. We might write some unit tests. But, researchers, we want to make sure that they can read the code and they'll be like, oh yeah, that's accurate. I believe that. I will build on top of it. So believability is very important. And what that means is that errors should be surfaced, logic should be clear, and the results then can be trusted because people are using our research to inform policy. Generally we think science should be accurate. Okay, so in my world, the big data pipeline is we have some messy data, we do some data cleaning, we run our analysis, and we get some results. And that would be loading GP records, so primary care doctor records or hospital data, doing some data cleaning, using a statistical programming language or a general purpose programming language to do my analysis. So commonly people are using R. I trained in Stata. Some people use Python. I always trash R. Are there any R users in the audience? Okay, excellent. It's terrible. Okay. There are 5 different implementations of classes in R for a reason. No one can explain why. I'm probably going to get a lot of hate now if that gets put on the internet, but oh well. And then we get some results. Anyway, okay, so everyone cares about the last 2. That's like the sexy part of epidemiology, if there is a sexy part. But this is where we spend most of our time. Like 90% of the time, I would say, we probably are dealing with loading records and doing data cleaning. And the problem with this is that everyone's kind of like rolling their own solution on how to do data cleaning. And this is a problem because there's just a lot of repetition. It's likely to be less accurate. And so I'm interested in making like open source, really high quality code, which can solve some of these issues. And for this talk, I'm going to be talking about something called Codeless. Okay, and this is the open source package. Okay, so we've all been to the doctor at some point in our lives, I'm going to assume. So imagine, you go in, you see your doctor, and what many people complain about is their doctor is typing onto the computer. Have you had this experience? Not looking at you. Yeah. Okay. So you might assume that what they're doing is they're just writing a free text explanation of like, oh, Johnny came in with a cough and, I did some blood pressure stuff, whatever it might be. And that is what's happening. From a GP's perspective, that is what's happening. But the computer systems have, essentially, it's a bit like autocorrect. So if you start typing pneumonia, it will open a drop down and be like, do you mean pneumonia? And you can click pneumonia. Okay, so from a GP's perspective, in routine care, that is just like, cool, that's helpful, right? I don't have to remember how to spell pneumonia. Excellent. Okay, but what it's actually doing under the system, under the sort of hood, is it's using a thing called coded events. So unfortunately, coded and codeless and code, we're going to be talking, they all mean different things. So if it gets a bit confusing, just stick your hand up and I'll try and explain. But a coded event is something where we have a number or a code of some sort, like an ICD-10 code or a SNOMED code, and it is associated with a disease state. Okay, so the idea is cough has one numerical value, which means cough, and therefore in the data you can look for everyone who's got that numerical value, which sounds like a great way of doing it. Okay, and so your appointment becomes something like this. So you get cough, blood pressure, fever, etc. And these codes, if you were to look them up, they all refer to those terms. Okay, the codes are in a tree. So cough, you've gone to the doctor with your cough. That's a respiratory symptom, so it sits under there. And then you've got chesty cough, allergic cough. So that sounds okay, except there are like hundreds of thousands of SNOMED codes. So I happen to know, I don't know what it says about me as a person, that there are 43 different types of cough in SNOMED, helpfully including no cough. So when we're doing studies, what we're trying to do in general is to take all of this data, all of the different ways that you might have represented cough in the data, and it collapse it down into like a binary state. Like, do you have a cough, 1 or a 0? And probably a date associated with that, which means you need to find all of the possible ways that cough could have been coded in the GP record, knowing that the GP has no idea what's going on behind the scenes in terms of the coding system. The computer does that for you. So just as an example, if I search in NHS Digital for pneumonia, for the different codes that could be, I get 2,000 hits. So that's a lot. So basically, as a result, epidemiologists spend so long writing these bloody code lists, okay? All of the different ways that you could, represent a disease state. I've literally lost days of my life to writing code lists. And it's a real challenge because they sort of change over time. You want to share them, you want to publish them. And the issue is, it's kind of boring, but it's something which is really important to do well. And going back to that pipeline thing, we want to make sure that the stuff going in is actually useful. And often no one's going to check it. So we've got to make sure it's correct. Okay. So I am now going to talk about why I'm here. Okay. So I am running this project called Codeless Tools. The idea is to solve some of these persistent problems that exist in epidemiology. There's still a fairly new project. And what I've decided to do is to write it in Rust. So I love Rust. So there's part of that. I love it. I think it's great. But because we know people are using different programming languages, I can write very performant, strongly typed code in Rust, and then I can expose R bindings, Python bindings. So like Python is calling Rust under the hood, R is calling Rust under the hood. And if we wanted to add different languages, we could. The sort of principle here is if you are running this sort of code, it should be running the same code whether or not you are like writing a web app that deals with code lists, or whether you're running your scripting language, which gives a result. And under the hood, it's using the same Rust implementation to make it a bit more standardized. Okay, cool. So now we're going to get onto the good stuff, the coding. Okay, so result. So often like data is messy. So I've made it sound like it's all very well structured. It's often not. Especially when you're combining different data sets like hospital data and whatever, GP data. So sometimes code data is missing, and that might be a null, it might be an empty string, it might be a none, it might be a nan. And imagine, like, for instance, with these code lists, one of the basic problems is if I send you a code list, I want to check that it's broadly correct. Now, the contents, we're going to ignore whether or not we think it's correct from a like scientific perspective. We just want to make sure that if I get sent an ICD-10 code list, that all of the codes in it look like ICD-10 codes. And there's various different ways, like rules of what they must look like. But for our simple example, we're just going to say they have to be between 3 and 7 characters. Okay, so that's like very simple. I would have done the actual rules if I had a bigger slide, but no, it is. So if we write this in Python, we could say, okay, we're taking a code, you know, if it's not code, we'll return a none. If it's short, we return a none. If it's over 7, we return a none. And if it's not, it returns a true. So this is not brilliant code, okay, but this is often what is done. So we need to remember that the caller needs to check this every time. So have we returned a none? And we also need to take into account, like, if there's an exception, like a value error or something. So what this means is errors become optional, easy to ignore. And I think we can agree that that's not ideal. Okay, so here's the same code, essentially, in Rust. And so what we've got up at the top is we've got something called a result, okay? And it's got 2 items within it. So the first one is an okay. So this is like, if it is okay, return this. And in this, I'm not returning anything. And if not, return an error, which is, in this case, a string. And so you can see that I can build it up. So it's very strongly typed. So result is the only thing that can be returned from this. So we're either returning something which is okay or something which is an error. There's none of this like issue with Python, which is often what people are using, where it might return an exception or a none, or it might just error in some other way. It's not ideal. Does that make sense so far? Cool. Okay, chaining. Okay, so I'm going to be talking about chaining. So we are at a functional programming conference, so I know you all probably love a bit of chaining of functions together. Is that correct? Lots of nods. Excellent. Okay, so in the real world, data is often written in R or Python. Oh, sorry, code is written in R or Python. And I will say R in particular is fairly functional. Python, often in this situation, is written in a more functional style. I would argue most epidemiologists don't know what an object is. They're just using Python as a scripting language. And so when I'm writing this open codeless tools, I am thinking about, using it in a functional way to a particular point. So on the right-hand side, you can see that I've got my raw code. So say someone sent me a list of ICD-10 codes and I'm iterating through them. I'm doing some mapping. I do a filter and then I run my validate code and I'm checking that it returns that okay result that we just saw in the previous slide. And then we collect them. Okay, so this is great. It's like a recipe. We have no mutable buffers, which is sort of how you might do it in a different language. There's no counters, and it just reads like a recipe. This is, I would say, quite good for people who are not used to reading Rust to like read it and understand, because most people who are writing statistical code will have come across a map, an iterator, a filter. Okay, so that's how we're using it. This is a slightly more complicated version. Say we want to validate many codes at the same time. We might create an empty list, iterate through many items, push errors into a list, and then check that the list is empty. Okay, and you could do that in Rust. And this is fairly readable. Okay, and particularly if you come from like an R Python background. So we could rewrite it though. So we could write it like this. I would argue that this is more correct. Okay, so it's easy. Well, for me, it's easier to read. So we've got a filter map, and then we've got, you know, various different things which happen, and we're dealing with the errors. But it's a lot less readable if you're not used to like dealing with actual programming code, not statistical code. And so whilst I feel that this is more correct, I've gone for the previous example because it's more readable. So that's why I say it's like functional-ish, because there is a line at which point I want to make sure that the code is as readable as possible, because other scientists are going to be reading it and being like, do I believe the results of this? Do I want to use this in my pipeline? So there's a trade-off, and who knows where that line is, but this is where, for this particular example, I've chosen to put that line. Also, not to mention most people, because they're not, lots of programmers don't realize about objects. Like they're already not know about self. So self.validate. Cool. Enums. Okay. Who here loves enums? There must be some, yeah. Okay. Controversially, not everyone put their hand up. Okay. Yeah. So enums are amazing. I think it's, very useful to have enums. And so if we're thinking about how we validate an ICD-10 code, and I've given you the rules, we could fail in a number of ways. It's useful to return an error that we can read and be like, I know how to fix this. So we could write this in Python. Okay. So in Python, each error is a generic value error that we're returning a response, returning a, custom string essentially. But it's confined to this function. So if I was to write a similar function that did something kind of similar, I'd have to write these all out again. And that is, well, I just don't like to repeat myself basically. So let's do something different. So in Rust, we can write an enum, and we've got this brilliant crate called this error, which essentially allows you to have enums and then add like the formatter here with some names. And that is extremely useful because every single time you need more errors, you find some other way that your code can break, you can write a new error. Does that make sense? How am I doing for time? Lots of time. I have a nice timer, which I very helpfully forgot to start. So, cool. All right, so let's move on to code list type. So I've mentioned SNOMED, okay, and I've mentioned ICD-10, but there are a number of other coding systems, and they have rules, as I said, about what you can do with them. So if we take ICD-10, so ICD-10 is that thing which is between 3 and 7 characters. It's actually a letter. It always starts with a letter, and then it has numbers after it. Occasionally it can have a dot. Sometimes it can have an A. So there's like a few different options. And importantly, if something is an ICD-10, it can be truncated. So it's sort of a tree in some sense. So if you had something which was like A1000 or 1001, you could truncate that to like literally cut it off and it would become like A100. So that is, it can be truncated, okay? Which is useful sometimes if you want to get a broad brush of like what sort of diseases people have. But you can't do that with SNOMED. So SNOMED, the codes, are between, I think it's between 6 and 18 numbers. And unfortunately, they don't really bear any resemblance to each other. So there's no way of knowing where, like if you, like one number doesn't relate to the parent it belongs to, and vice versa. Okay, so with codeless types, I have made an enum for the different codeless types. And that has some advantages. So I'm not brilliant at spelling, so I could misspell SNOMED. So this is in sort of traditional epi, you would only find that this was an error, and when you hit that part of the code in the script and was like, I don't know what to do with this. And that's a really big problem, because when we were dealing with like a lot of the COVID data, it was like taking 8 hours to run an analysis. You don't want it to error at like hour 3. Like, it's just a waste of time. So you want to catch them early, which is why Rust is really good for like finding those errors before it's even, like, it just won't compile. So immediately you've got your answer. So I made a codeless type. So SNOMED, ICD-10, and a couple of others. And then we've applied this rule. So I could have, this is again Python, and it's like, this one is R. So R has this like backwards, I don't know, it's like declaring a function. Anyway, it's a bit complicated. And very confusing, because it's like, you go like, it's over there. But if we write that as Rust, we can express the rules as pure functions on the enum. So it means that the domain logic is explicit. You can just read it. And so we've got our codeless types up here. And then we've got, can they be truncated? And also with ICD-10, you can add an X as the 4th character. And yeah, so we can add that. So we can just have quickly look at that and be like, oh yeah, I can do that for this particular type of code list. But I don't see it for like SNOMED codes. Cool. Cool. All right. So we're going to be talking about pattern matching now. So how many people use Scala in this room? Wow, that's a lot of you. So I think this is similar to case. I'm going to look at you, Zainab. Is that correct? Because you know both Rust. Yeah. So match is this keyword that we have in Rust, where we want to essentially like match a thing, or I guess case a thing in Scala, and make sure that we've dealt with every possibility, every part of a decision tree. Okay, so let's use this as an example. Okay, say, and this is made up, say for example, I've got a code list, actually let's just keep a code. I have a code, a SNOMED code or an ICD-10 code, and I want to check it's valid. And valid, as we talked about, is broadly, is it just the right characters or the right sort of format? And let's say I care differently about different types of errors. So if it's the wrong SNOMED, like length, or, you know, ICD-10 length, I really care about that, because we know that that won't be in the data. So we want it, like, something has gone profoundly wrong if something like that has happened. And that actually happens a lot, because people often mix ICD-10 and SNOMED codes together in the same code list. So that's a critical error. It's just the wrong length. Shouldn't happen. But maybe we don't care about some other, like, invalid code contents. Maybe it's just, I don't know, you have a list of ones that you're interested in and you just don't care. We'll just skip it if we get this particular type of error. And then we also want to count for other errors. So what we can do with a match is that we can inspect the results of our validate code, and then we can match the response. So we can do, you know, okay, so that's fine, we're happy with that. We can do a critical error, and so we're matching if the error that we get back is of the type code list validator error, invalid code length. And then we're going to panic and be like, okay, if it's got to this point, let's just crash the whole thing. Whereas if we get to the invalid code contents, maybe we're like, okay, we're just going to print an error. And then, you know, we can look at the logs later and try and figure out exactly what's gone wrong. And it's sort of similar with, we can do a different type of log for the other one. I'm just going to drink some water. Please don't listen while I drink water. Okay, So what's great about Rust and other programming languages, but I'm here to talk about Rust, is match lets you make those branches explicit. So it's not just like, if you get this particular error, or if you get an error, crash it. Or if you get this error, just log it. You can be ultra specific about it. Ones that you care about, ones that you don't, ones you want to log. And that is super helpful, particularly when you're dealing with like large amounts of data, which is messy. Cool. So that's like a whistle-stop tour of the different ways. Well, there are many different ways that you could use functional-ish programming in Rust. But these are the things that I think are cool. So I really like the result as a value. Actually, under the hood, result is just an enum. It's just a different type of, like, it's just an enum, basically. And of like an OK or an error. Chaining. So transformations expressed as pipelines without mutation. Really useful, but as I said, we need to make sure that the code is readable. And so readability is always the sort of like guiding light of scientific programming, or it should be. So we want to make sure that we are keeping that, you know, right up close and sort of making sure that that's really is our guiding light. Enums. So all possible states are encoded and they are enforced by the typing system. So there's this thing when you use Rust, like when you first start using Rust, you call it like fighting the compiler. So, which is definitely true. So you're nodding. So has anyone else spent any time fighting the Rust compiler? Yeah, there's a few people who are nodding. So it's this very annoying experience where you can't even run your code because it's just will not compile because there's some pattern that you haven't matched or there's some error. And so, enums are really useful and they often, like the compiler will say, okay, you haven't thought about this possibility. What happens if your code returns an error here? And you have to be explicit and think of some solution for that. Maybe that's crash the program. That's a completely reasonable response, I would say, depending on what it is. And then we've got pattern matching. So this is just, you know, again, kind of the same thing, but just explicitly handling every outcome. Cool. All right. I'm going to pause here and then I'm going to go on to how we kind of put this all together. Does anyone have any questions at this point? No questions. Okay. Have you understood? Okay, cool, nice. Okay, I've got some thumbs up. I like this. A bit of audience participation. Yep.
How often do you go back on incorrect codes for fixing those?
Fixing
the original data source.
Oh, basically never. Yeah, so the question, if anyone didn't hear it, and tell me if this is incorrect, is how often do we go back and fix the original data source? Is that correct? Yeah, basically never. I mean, the volume of data is just so massive. So if we think back to our cough example, like I think I put 4 or 5 different rows of data for that particular instance. In reality, that might be 10. So imagine how many, I think there's I can't remember what the statistic is. It's something like 1 million appointments a day or a week. But anyway, it's a large number in the UK that all gets not compiled, it all gets put together in this way. And so it's just basically impossible to go back. And kind of the principle always in research data analysis is like, don't touch the original data source. You can create a clean data source from the original data source, but you never go back and touch the original. Yeah, it would be, sometimes I do like fantasize that we would be able to go back and change some of the data, but alas, we can't. Or we shouldn't, I suppose. Any other questions? Yep, go for it.
Yeah, so my question is 2 small questions. You mentioned that like the whole pipeline usually takes up to 8 hours to each run. And what time or percentage rate spent in base buildation?
Well, that very much depends which group you're part of. So which like research group so people are using the same data to run different research studies. There is no explicit way of like how you must write your code. So people are using different programming languages and different kind of environments. And so there is no kind of like standard way. It's hard to say. I would say probably a lot of research groups do very little validation. And that's a real problem, because if you get these huge pipelines, you don't want to find out like 3 hours in that you've put in an ICD-10 code, which is actually a SNOMED code, and the whole thing just like blows up. That's
okay. Second small question.
Yep.
You said that previously, like the general consensus that like most people use Python for that. Have you seen any kind of performance improvement, or you'll be talking about this right now?
I'm not going to be talking about that, but it's a good question. Yeah. So I don't want to give you the false sense that everyone's using Python. That is unfortunately not the case. There are some groups which are like doing more kind of machine learning AI type work, which are very Python centric. I would say most people are using R, or there's the occasional use of like MATLAB or Stata. Those are kind of tricky. There's a bit of a move away from them because they're more proprietary. Like you have to pay for a license, so people want to move to more open source type of languages. So yeah, I've forgotten what the original question was now.
So have you seen any performance?
Yes, performance improvement. So this is an open source library, which isn't like hugely used at the moment. So that's something we're hoping to address. But yeah, like there are some bits where for this whole project, I got really inspired by Polars. Has anyone used Polars? Got a few nods. So Polars is a package that you can call from various different languages, but more importantly, you can call it from Python. And it's Rust under the hood. So it's a data frame library for like tables and stuff. And it's hugely efficient. And so I rewrote some code, which was like taking kind of like 2 hours to run in a Jupyter notebook in Python, into a package that used Polars under the hood. And it basically went from like 2 hours to like 5 minutes to run the whole thing across like millions of rows of data. So yeah, you can get some real improvements just by that. And so I took inspiration from this like amazing package, Polars, and was like, okay, well, we can do something, well, not as good, but the similar principle, which is like, let's write it in Rust and let's expose it to a slower, less performant language. Any other questions? Cool. All right, let's look at it. Okay, so far we've concentrated on just one code. So is it correct? But back to the cough example, we're dealing with like 43 different types of cough. We're rarely looking for just one code. So we use code lists. So code lists are exactly what they sound like a list of codes which represent a disease state. So maybe there's like 50 codes which represent like diabetes, type 2 diabetes. Okay. And so you might, when I first rocked up in epidemiology and did my first study, it was very much, this was the conversation. Oh, you need a code list for pneumonia. We don't have a code list for pneumonia. Why don't you speak to Sharon up the corridor? She did a study 3 years ago using pneumonia. She might give you the code list and maybe you could use it in your things. And maybe you get it, maybe you don't. So they were like emailed around, put on shared drives and then things, or printed at the end of a PDF on a paper, which is an absolute nightmare. So it's really difficult to find out like what people have actually used to represent diabetes, pneumonia, whatever it might be, HIV, things which are super important to get correct. And so this has kind of been, it's a long-standing problem that I think most epidemiologists would say is an issue. So again, you get code lists. They may come to you in like any other format, well, many formats. One of the sort of things I'm hoping to do with this project, again, we're early days, is to try and move people to like standard practice. And I'm not the only person working in this space. There are other groups. There's the Bennett Institute in Oxford, which is doing some really good work in this space. There's the AI Centre for Value-Based Healthcare that's at King's that's also doing some really cool work in this space. So we want to move to a place where code lists are standardized. They come in a particular format. They can be shared. And more importantly, that they have like useful metadata around them, like who made the code list, for what purpose, and what did they use to decide. So you can imagine if you are going to think about a study about cough, you might define cough to be differently important if you're dealing with flu or COVID. Okay, you want infectious cough. You'd obviously want to remove allergic cough from that scenario. But if you were doing a study where you were really interested in allergies, you'd probably want to get rid of the pneumonia type coughs. So that might be, so when you get sent a cough code list, you need to know that. You need to know for what purpose you've been, it's been created. And so that's part of what we're trying to do with code list tools. That was a long explanation. Okay, so let's go on to the next slide. Okay, so code lists are shared in CSV files and JSON files. They're obviously shared in lots of other ways, but we're just imagining in an ideal scenario, they're only shared in 2 formats. Okay. So on the right-hand side, we've got our wish list. This is what I wrote down, which is I would like there to be an automated, standardized way of loading a code list, and you have built-in validation. So if you load a code list, it immediately runs a validator over it, being like, you said this is a SNOMED code list or an ICD-10 code list. Does it fit the format of what we know about what these codes should be? And it just fails immediately. So it's basically a guarantee. If a code list loads into your script, it is correct. Sorry, I'm running slightly late. Okay, so the entry point of the API surface is one entry point. So scientists are going to call, ignore the factory, .load code list, and then point it to a path. But under the hood, the code list factory is going to have load code list from a CSV file, load it from a JSON file, which you are not aware of. And then we're going to use, I'm going to skip over that, a pattern. So we're going to use our matching to basically pull out the extension from the path and then to run the right function. So you can guarantee that if you get an OK from this, it's a code list which is valid according to your rules. And if you look at the result here, we're returning either a code list or a code list error. And if we go on to one of these self.load code list from CSV file, you will see, oh, that's a bad one. This is part of it. You are returning basically essentially the same code list error. So it basically allows the error to bubble up from the smaller function into the main. Cool. I'm going to skip over lessons learned because I feel like we talked about it and I'm running out of time. Oh, and if you want to get in touch, I do also run Women in Rust. And so if you know anybody who might want to join, please get in touch. And then if you scan this, it will go to my website and I've got a blog and I write about things to do with health data. And that's it.